Hello everyone. Today I would like to present the proof of sequential compactness theorem in this video. In this video, we will first introduce what is sequential compactness. Then we will proceed to the difference between closed and sequential compact. They have some relationship, but they are not the same. And last, we will look details into the proof of sequential compactness theorem. So, what is sequential compactness theorem? I have found some data from Wikipedia. First, sequential compactness theorem is also known as Bolzano Weierstrass theorem. In 1817, Bernard Bolzano proved it as a lemma in the proof of the intermediate value theorem, which is another important theorem in mathematics. Then 50 years later, Weierstrass proved it again because of its significance. This theorem has since become an essential theorem of analytics. So it had been proved individually again. And now let us see what is sequential compactness. Sequential compactness means a set of real numbers S, provided that every sequence in S has a subsequence that converges to a point that belongs to S. So we have to prove that every subsequence of the sequence in the set has converges to a point in the set. So what is subsequence? Subsequence is if there exists a strictly increasing function f so that Pn is equal to Fn for all n in the natural number. Here is some example of the subsequence. You can see that the second example is an, then we can say n is natural number. So we have a1, a2, a3, a4, a5, a6, and so on. Then we can have its subsequence to be bn, which is equals to an squared. So this is also a subsequence of an. Now let us look at the difference between closed and sequential compact. Just now we have seen the definition of sequential compact. Now let us look at the definition of closed. A subset S of the real number is said to be closed provided that an is a sequence in S that converges to a number. Then the number is also in S. We can say this subset, this S, is closed. So we can see that closed is a condition on a convergent sequences, but sequential compact is a condition on every sequences. You can see, right, the definition of closed is sequence itself that converge to a number that we want the number have to inside the set itself. But sequential compact, we want to have the subsequence of every sequence that have converges to a number that belongs to the set itself. So these two have some relationship inside, but they are different. And this is an example. The set S from 0 to infinity is closed but not sequentially compact. You can prove this by just using the definition. Alright, let's now go to the proof of the sequential compactness theorem. The theorem says a set is sequentially compact if and only if it is closed and bounded. One thing to highlight is this theorem is an if and only if theorem, so we have to prove it at the two different directions, which is the first direction. If a set is closed and bounded, then it is sequentially compact. And the second direction is if a set is sequentially compact, then it is closed and bounded. But for this second one, we will like to prove in a different way, which is it contrapositive. That is, if a set is not closed or not bounded, then it is not sequentially compact. These two are the same, but the later one will be easier to prove. So we will prove these two in the following. For the first one, if a set is closed and bounded, then it is sequentially compact. So what is closed and what is bounded? Well, we have seen the definition of closed before, which is if AN is a sequence in S that converges to a number, then the number is also in S. And what is bounded? Bounded means that a sequence AN is said to be bounded provided that there is a number M such that the epsilon of AN will be smaller or equal to the M for all N. Then we can say that the sequence is bounded. So to prove this one, we first assume a set S which is closed and bounded, right? Because we want to prove that if the set is closed and bounded, then it is sequentially compact. So we assume the set is closed and bounded first. Next, we have to define a sequence AN which is in the set. And since S is a bounded set, which we assume, so AN is also a bounded sequence, right? Because we always can find a number M which is bigger or equal to the sequence. And we have this theorem: every bounded sequence has a convergent subsequence. So this bounded sequence AN will have convergent subsequence. And since the set S is closed, so the convergent subsequence must converge to a number, to a point inside the set, right? Because the subsequence is convergent, so it will converge to a point, and because the set S is closed, the point must be also inside the S. And therefore this proves that S is sequentially compact. Because we have for every sequence in the set, it has a subsequence that converges to the point inside the set. So it's sequentially compact. Then we prove the first direction. Now let's move on to another direction, which is if a set is not closed or not bounded, then it is not sequentially compact. And this is the contrapositive of this theorem, says that if a set is sequentially compact, then it is closed and bounded. Well, we have to take note that because we take it contrapositive, so we have to change the closed and bounded to not closed or not bounded. Okay, so in this definition, we have to prove in two cases. One is the set is not closed, and another one is the set is not bounded. Then we can say that it is not sequentially compact. These two cases, we will prove it one by one. Now for the first one. Case 1. The set S is not closed. From the definition, we have there exists a sequence in S that converges to a point that not in S. This is a definition of not closed. And we have a proposition that said that if the sequence is convergent to a limit, then every subsequence will also converge to it. Therefore, we have every subsequence of n also converges to a point that is not in S. Previously, we said that we have a sequence an, the sequence is converges to a point A, but the A is not in S. Therefore, we can prove it by this proposition that every subsequent of this an will also converge to A, but the A is not inside the set. Therefore, the set is not sequentially compact because the point is not belongs to the set. Because the definition of sequential compactness is that every sequence that has subsequence converge to a point inside the set. But this one, we can clearly see that they converge to a point A, but the A is not inside S. So we are done for case 1. Now we move on to case 2. We assume the set S is not bounded. Without loss of generality, we said that S is unbounded above. You can also say it is unbounded below, but we will use this definition to prove that if it is not bounded, then it is not sequentially compact. Since S is not bounded, so we have, from the definition we have, for every n, there exists an element of S that are bigger than n. So we consider a subsequent Bn, which is equal to AFN, where the f is a strictly increasing function. Well, this is also the definition of the subsequence, and therefore we can say that Fn is larger or equal to n. Because Fn is a strictly increasing function, so Fn is larger or equal to n. And also the Bn will larger than Fn, which is larger or equal to n for all n. This is because we have An is larger than n for all n. So AFN will larger than Fn. And this one will prove that Bn is also unbounded, because Bn will larger than n for all n. Therefore, the definition is unbounded, and so it does not converge. And this one proves that S is not a sequentially compact. So let us have a quick recall for what we have discussed in this video. First thing is the definition of the sequential compact, which is every sequence An in a set that has a subsequent that converge to a point inside the set. Then we can say that the set is sequential compact. And the sequential compactness theorem says a set is sequentially compact if and only if it is closed and bounded. Alright, that's all for the video today. Thanks for watching.